We've talked about it a little, but now let's dive right into the philosophical implications of quantum theory and quantum mechanics. They're very profound, and in fact, they're not fully understood. Let's start with a quote from Bertrand Russell. "Ordinary language is totally unsuited for expressing what physics really asserts, since the words of everyday life are not sufficiently abstract. Only mathematics and mathematical logic can say as little as a physicist means to say." That's very artfully put. What is he saying? Well, he's saying what we learned with antimatter, that you actually had to trust the solutions of the wave equation in two symmetric forms to believe that there was a mirror form of matter with opposite quantum properties called antimatter. And then you went out in the universe a decade later and discovered that antimatter does exist. It is real. So physicists have learned to trust the mathematics of their successful theories. And unfortunately, words can only do so much justice to the situation of the physical world as described by mathematics. The quantum mechanics view is this: all matter and particles have wave-like properties. This is the wave-particle duality. And those particle-waves are described in a probabilistic matter. The electron is not whizzing around the nucleus. It has a fuzzy probability distribution describing where it might be found. And this is what allows for the seemingly impossible phenomena of quantum tunneling. Some properties come in packages together, and you can't simultaneously pull them apart and know them with arbitrary precision. This is the Heisenberg uncertainty principle, and it underpins quantum theory, and it truly seems to underpin the physical world we live in. It's not an artifact, it's not a mathematical tool, and it's certainly not a problem with measurement itself. It's built into the world. So, position and energy, and position and momentum, and energy and time are examples of these pairs which we cannot both know simultaneously perfectly well. And then, unavoidably, the act of measurement of any microscopic system, particularly single atoms, fundamentally alters the system. Also, the act of measurement can cause what's called entanglement, information exchange in the measuring tool and the thing that's being measured that alter that particle's state. The traditional interpretation of quantum theory, philosophically, was called the Copenhagen Interpretation, and its main architect was Niels Bohr. His view was that the wave function only describes a subjective state of knowledge. It's not itself real. We'll talk about Schrodinger's cat. Schrodinger's cat can be both alive and dead. Wigner, another physicist's friend, can see a different wave function than Wigner. And there are no paradoxes. These are just tying yourself up with words. The collapse of the wave function when you measure the position of something is subjective. You can't transfer information faster than the light speed anyway. And the uncertainty principle defines the limits of certainty. Bohr said that science is only about predicting the outcome of experiments. All additional questions are metaphysics. In other words, he really thought we should shelve all ideas about talking about underlying reality and what does quantum theory tell us about that. He said the wave function is all you'll get. And of course, as we've seen in the modern era, that's turned into the shut up and calculate school. Here we see some of the quotes. The people who worked on quantum theory knew exactly how strange it was. We start with Bohr. If quantum mechanics hasn't profoundly shocked you, then you haven't understood it yet. And a very related sentiment from Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. And remember, these are the physicists who are the architects of the theory saying that. So us mere mortals that are just studying it are excused for being completely confused. And then we have probably one of the greatest mathematical physicists of the current age, Roger Penrose, saying quantum mechanics makes absolutely no sense. In the flowchart on the right, we see the foundational philosophical divide between people who think and talk about quantum physics from the time of its formation. There are essentially the realists and the anti-realists. The realists just essentially say that that's all there is. The wave function is all you get. The anti-realists say that quantum mechanics is probably not the final or foundational theory, that there's a deeper theory which describes reality that we're looking for. Einstein was in this school. Einstein believed in what were called hidden variables. That was things that were not discernible through an experiment, but represented a deeper view of reality. And so, in a sense, he thought quantum theory, as well as it worked, was smoke and mirrors, or a veil over reality that could be operationalized and used quite usefully, but was not giving us the ultimate truth. We can talk about experiments, both actual and hypothetical, that illustrate some of the weirdness of quantum theory and draw out some of these philosophical issues. It's well known that you can shine particles, if you consider light a particle, from a single light source through two slits, and they will go to a screen behind. If we consider light to be a particle, a photon, which we do, then the light can only travel in two directions and end up at two places, one shown here and one to its right. On the other hand, if light is a wave, which it is, remember the duality, then light will pass through the two slits and the waves will interfere and produce an interference pattern that you see at the bottom of the diagram. That's classic optics that was seen 200 years ago. So the pattern on the screen is an interference pattern characteristic of waves. So light is clearly a wave, not like a particle. So what is actually happening in the situation on the left? We can slow down the light source on the right so that it produces just one photon a second. We can do that actually in a lab situation. And so as one photon a second comes from the light source and may pass through a slit or may hit the barrier between the slits or go through the second slit and so on, the photons still only land on the interference peaks. So even generated one photon at a time, the experiment gives the pattern on the right. What is going on? How can a single photon knows that it's not supposed to go to certain places and go to others? How can one photon, which should logically travel in one of two straight paths on the left, end up back at the center? This is very strange. This is the double slit experiment, and it really draws out the conflict, if you like, between the particle-wave duality of nature. It's very non-intuitive to have a combination of wave-like and particle-like properties. Clearly, at low intensity, the interference pattern is still being built by photons arriving one at a time. But how does one photon know that it's part of a two-slit experiment? Does the photon see or feel out both paths simultaneously and then sort of head towards the right place? Very strange. We can speak of the wave part just by describing the probability distribution where photons may land, and quantum theory says that's all we can do. What about Schrodinger's cat? This is now a thought experiment. You recognize that quantum physicists love thought experiments. Some of the experiments are hard to carry out, and you can elucidate problems or issues with the theory with a thought experiment. In 1935, Edwin Schrodinger designed an experiment to illustrate the difficulties with this prevailing interpretation, the Copenhagen Interpretation. So we imagine a cat and a flask of poison placed in a sealed box along with a radioactive source. If the atom decays, it triggers a mechanism that shatters the flask and the cat dies. And it does so with 50% probability in a period of time. It's easy to arrange a radioactive source so that in a period of time it has a 50% chance of sending out a particle that will shatter the flask. So at the end of that period of time, logically there's a 50% chance that the flask was shattered and the cat is dead, and the flask is not shattered and the cat is not dead. The question then is, how do we describe the cat before we open the lid of the box to see what actually happened? This is very strange. In the quantum world, this is a wave function describing this, and that's why physicists talk about collapsing the wave function. So in quantum theory, the cat literally has a superimposed state of live and dead equal probability, which only collapse into one definite reality when the system is open to observers. Maybe curiosity does kill the cat. And even then, we can have two different interpretations. The classical or Copenhagen view of the situation on the left is that the cat, until we look inside the box, until the end of the experiment, has to be described logically as both alive and dead. However, in the 1950s, Hugh Everett came up with the many worlds theory, not only of quantum physics, but of the universe as a whole, which is that every time there's a quantum probability, which is essentially all the time, the universe bifurcates into two paths, and then two more, and then more and more and more, and each outcome is real in a multiverse of endlessly branching options. And so there's one option where the cat is dead and one where it's alive. And then when something else happens further downstream, the movie splits again. It's a dizzying idea, but logically also consistent with the experiment. Here's another actual experiment that's receiving a lot of attention these days, the idea of quantum entanglement. What is quantum entanglement? This is a very foundational issue, again, of quantum theory seen routinely in the lab, where separated parts of a quantum system can be entangled. They can share information and be associated with each other. And so the possible outcome of a measurement at one position depends on the result of a measurement at a different position. And it obeys conservation laws. And we actually see in an image just from July of this year, the first ever image of photons in a quantum entangled state taken at the University of Glasgow. So this is real. Well, what does this mean? It means that physics is non-local, because if we can have entangled states of photons that are now physically separated in a lab, possibly by large distances, then somehow if one photon knows about the other photon, that information must be transmitted instantly across a space, rather than being limited by light speed. That is non-physical. That violates causality, actually. And Einstein called this spooky action at a distance, and was part of the reason he was uncomfortable with quantum theory. Now, this has worked its way into various experiments. Quantum cryptography actually uses this method. So in this cartoon, we see a version of this experiment where entangled photons are sent, one to someone called Alice and another to someone called Bob. Alice and Bob are quite far from each other, and the photons are too, but they're entangled. And so when Alice randomly chooses to measure the polarization or orientation of her photon and doesn't tell Bob, Bob can also randomly choose to measure the polarization of his photon and not tell Alice. But Alice and Bob both realize that the results of their measurements are correlated because the photons, even at that distance, are still intimately linked. And that's action at a distance. Very strange. So quantum mechanics has very important implications for epistemology and metaphysics, and let's go through them quickly. Quantum mechanics implies that almost no event is strictly impossible. We see this quote from a physicist at CERN, quoted in the New York Times. The random nature of quantum physics means that there's always a minuscule but non-zero chance of anything occurring, including that the new collider could spit out man-eating dragons. Well, obviously he's making a joke. But what he's saying is that things can happen that are exceptionally unlikely, but with very low probability. They do not violate a law of physics. If you have an iPhone on a table in front of you, there's a tiny chance, and a physics student, sophomore level, could probably calculate it, that iPhone, the energy state of all the atoms in it, would spontaneously align and it would jump off the table by an inch and then fall back down again. That is not against the laws of physics. It's just an extremely unlikely outcome of a set of quantum probabilities. So this is a strange way of thinking about things that can and can't happen in the universe. Quantum mechanics is also undermining our notions of causality and determinism, because physics can no longer tell us rigorously what caused this event. In the classical case on the left, we know that the dominoes falling will lead to an effect. We know that when Macbeth brings out his knife and uses it, someone will die. In the analogous world of quantum physics, the causality, or even the direction of time, is no longer so obvious. Cause and effect are entangled or potentially even reversed. With the Copenhagen Interpretation, which is still the conventional philosophical view of quantum theory, human consciousness seems to have a distinct and important role. As we've seen, the cat is both alive and dead until you open the box. What is it about opening the box that changes anything? Because clearly the radioactive decay has already occurred or not occurred, and so the outcome is known. And we see this in the quote of Wigner. The very study of the physical world leads to the conclusion that the concept of consciousness is an ultimate reality. it follows that the being with consciousness must have a different role in quantum mechanics than the inanimate object. Why should an observer be important in the physical universe? What happens in a universe with no observers? What happens in parts of the universe where there are no people to do experiments? Do things behave differently? This is very strange. The wave function being the ultimate reality implies there's a serious limit to human knowledge, and that's been known for decades with the quantum theory. We just have to accept this limit. And finally, quantum mechanics challenges our assumption that ultimate reality will accord with our intuition. The world doesn't have to be sensible, it's telling us. We have ideas about what is normal and reasonable when we interact with the world. Quantum physics is telling us something different. Feynman said, "I think it's safe to say that no one understands quantum mechanics. Do not keep saying to yourself, if you can possibly avoid it, but how can it possibly be like that? Nobody knows how it can be like that." But we've seen, by its utility, it really is like that. And that's the end of this module.